So we're going to start with this unit by talking about ionic bonding. So just for bonding in general, bonds, of course, are what keep atoms together in either molecules or in ionic compounds. And fundamentally, chemical bonds are electrostatic forces. What this means, this has to do with the interaction between charged particles in an atom, specifically the protons and the electrons. And it's going to be about the balance between the attractions and the repulsions between those protons and those electrons. So for example, let's take a hydrogen molecule, right, H2. If you had a hydrogen molecule, H2, there are going to be some protons and there are going to be some electrons. Now, in this bottom picture, just kind of standard H2, you're going to have two protons that are going to repel each other. You're going to have the two electrons that repel each other. But the protons and electrons, all those different combinations are going to attract each other, right? A similar situation if you had something even a little bit stranger like H2+. But the point is you have all these different interactions, plus plus, minus minus, plus minus, and you're going to have to basically add up all of those different attractions and repulsions to figure out kind of the strength of the overall bond here. So one way we can show this is to use a graph that looks like this. So this is a very important graph to understand. On the x-axis, what we have here is we have the internuclear distance. Basically, this is saying how far apart are the two atoms, how far apart technically are the two nuclei. So if you're over here on the left, that means that the two nuclei are basically touching each other. And if you're getting further here to the right, the two atoms are getting farther and farther apart. On the y-axis, what you have is the potential energy. And what 0 represents is if the two atoms were infinitely far away, right? Basically, if they didn't know each other, the other atom was there, if they didn't interact at all, basically they have 0 potential energy between the two of them. If you are in positive energy, positive potential energy, that means that they actually are like repelling each other and they don't want to really be next to each other. And if you are negative, that means that they're actually attracted to each other and there's a more positive attraction between them. So what's the idea here? Well, the idea is that you'll notice is that if atoms get really, really close together, then they're going to have a net repulsion. Why? Well, because the nuclei are going to be too close together, and so that repulsion is going to be more important than any of the attractive forces. Obviously, if the atoms are really, really far apart, then the protons and electrons can't have any of those positive interactions. But somewhere in between, and in the case of a hydrogen molecule, right around 74 picometer separation, it turns out that's kind of when you reach this kind of Goldilocks best in the middle, right? So if you're 74 picometers away, the nuclei don't repel each other too much, and yet they're close enough where the attraction between the protons and electrons can become maximized. So again, too far out here, as they come closer, the electrons start to attract more to the opposing proton. You reach that kind of minimum of energy at 74 picometers, and then again, if you get any closer than that, then the repulsion is going to take over. And so this is sometimes called a potential energy well, right? Like a well is something that you dig into the ground, and so this is kind of like the bottom of the well there, which is kind of like the ideal distance between the two hydrogen atoms. So in short, a bond is going to occur when you have more attraction than repulsion, right? So that's kind of the bottom of that well there when there's a lot of attractive forces. A bond does not occur, though, when you have more repulsion than attraction. So again, when there's too much repulsion, if the two atoms get either too close or if they're really, really far away and there really isn't any attraction at all, then there isn't going to be a bond. All right, so the key idea with bonding is that we need to think about the valence electrons, right? Atoms have lots of electrons, but let's just focus on those outer shell ones. There's two main modes with which this happens, ionic bonding and covalent bonding. Ionic bonding is when electrons are transferred from metal to nonmetal. That's what we're going to focus on today. And then later on this unit, we'll talk about covalent bonding when electrons are shared between two atoms. The goal, of course, is that you want to get the electron configuration of a noble gas by adding, losing, or sharing these electrons. So as a shorthand way of representing these atoms and their electrons, we have what we call Lewis symbols or Lewis dot symbols or Lewis dot diagrams, depending on what source you're looking at here. Basically, each dot around the atomic symbol represents a valence electron, and you can see these here for the first 8 elements of period number 2. So when you do this, make sure you draw the dots separately, the first 4 dots separately before you pair them up. And again, the idea is that you want to use this mostly for the elements that are going to become like noble gases. What that's saying basically is use these for the main group elements, so 1A through 8A. The transition metals and the lanthanides and actinides, Lewis symbols don't typically make a lot of sense necessarily for those. All right, so magnesium, silicon, and phosphorus, what would their Lewis symbols be here? So you're going to start with the symbol. So magnesium, of course, is Mg. And then magnesium is in group 2A, so it's going to have 2 dots. So I will draw them as such. Now, where you draw the 2 dots doesn't really matter, so you can draw them top and right like so. You could draw them left and right. Again, there are 4 possibilities, up, down, left, right, so just draw them in 2 places. All right, silicon is Si. It's in group 4A, so it's going to have 4 dots, so 1, 2, 3, 4. Now, with silicon, you don't have a choice. They do have to be in those 4 different spots because, well, the first 4 have to be drawn separately. Lastly, phosphorus is in group 15 or group 5A, so it's going to have 5 of them. So the first 4, 1, 2, 3, 4, we're going to draw separately. And then the last one you have to pair up here. So again, just pick one of them to pair up. Again, which one you pair it up with doesn't really matter. So I could have drawn it this way, but I could have also drawn it 1, 2, 3, 4, and then paired up the one over here on the right. Again, it doesn't really matter. All right, so the idea behind an ionic bond is that atoms are going to lose and gain electrons. Again, the goal is to become like a noble gas. They aren't technically noble gases, right, because the nucleus hasn't changed. The nucleus is still the same number of protons, but the electrons might look like that of a noble gas. Now, one thing that's important here is a lot of students think it's just about the transfer of electrons, right? When I say that word ionic bonding, it's, oh, electrons are transferred. And that's true, electrons are transferred, but that's actually not really where the bond is. The bond comes in that after you transfer the electron, now that you have one thing that's positively charged and one thing that's negatively charged, they're now going to attract each other, right? I mean, that's what positive and negative charges do, right? We can call this an ion pair when you have a cation and an anion that attract each other because of their opposite charges. And it's that attractive force that really is going to be the ionic bond. Now, one other thing to note is that, again, a lot of times, especially when we do these examples, we'll have like one cation and one anion. But in reality, that's not really what's going on. And I think I've mentioned this in this class before, but ionic compounds are never just one cation, one anion. No, instead you have many, many cations, many, many anions in something called an ionic crystal. So let's say, for example, we're reacting sodium with chlorine. Sodium, of course, is a metal. It's a very reactive metal. Chlorine is kind of a yellowish, greenish gas. The reaction actually releases a lot of energy when you do this. But what you form is table salt, right? Just ordinary table salt. But as you can see here in this picture, table salt, a crystal of table salt, is not just one sodium and one chlorine, or 2 sodiums and 2 chlorines. No, it's actually 10 to the 23rd sodiums and 10 to the 23rd chlorines that form into this thing called a crystal, or crystal lattice, which you can see here. So it's a repeating pattern of all these pluses and minuses that arrange themselves to kind of maximize the attractive forces and minimize the repulsive forces. We'll talk more about crystal structures next semester as well. All right, so what we can do here then is we can show ionic bonding using Lewis dot symbols. Again, this is going to be mostly useful for S and P block elements. You might see it with the transition metals, but it's kind of unusual, I would say. So what you can do is you're going to draw the Lewis dot structures for the elements, and then you're going to show how the electrons are transferred from metal to non-metal just by drawing arrows. So for example, let's say that we're looking at magnesium and nitrogen here. What would the ionic compound formation look like here? So I'll start by drawing out a symbol for magnesium, Mg, 2 dots, as we've already discussed earlier. Nitrogen is in group 15, just like phosphorus is, so 1, 2, 3, 4, and 5. And now what we want to do is to show the ionic bonding. So again, the way the electrons are transferred is that they always go from metal to non-metal. So in this case, magnesium is going to give its electrons to nitrogen. And so I can just draw arrows showing that idea. So magnesium is going to give one of its electrons. Magnesium is going to give another one's electrons. Now, at this point, magnesium's happy because it's gotten rid of its outer electrons, and it will now have a noble gas configuration. But nitrogen, even though it's gained 2, isn't quite happy yet for hopefully obvious reasons in this picture. Specifically, nitrogen still needs one more electron. So what's the solution here? Well, clearly I'm going to need another magnesium. So magnesium, draw another 2 electrons in, and magnesium can give its electron to nitrogen. And now nitrogen's happy because it's going to have 8 valence electrons. It's going to be like a noble gas. But of course, the problem is that magnesium has this extra electron. The second magnesium does. So it needs a place to donate its electron to. So I'm actually going to have to bring in another nitrogen here. I think at this point, most of you guys can see where this is headed. Because after magnesium gives its electron to the second magnesium, sorry, to the second nitrogen, the second nitrogen is going to need some more electrons to bring in a third magnesium. And this, of course, will complete our picture. Because now this third magnesium can donate its 2 electrons to nitrogen and fill its outer shell like so. And so what is the net situation that we have here? Well, we're going to have these 3 magnesiums. Again, they've all lost their valence electrons, so that's why I'm going to kind of just draw it empty. But importantly, they've each, since they've lost 2 electrons each, have gained a +2 charge. And then we're going to have the nitrogen with its full outer shell, 1, 2, 3, 4, 5, 6, 7, 8. And it's going to have a -3 charge. And there's 2 of those. Okay. So 3 magnesium, 2 pluses, 2 nitrogen, 3 minuses. And again, now that we have some positively charged and something negatively charged, they're going to attract each other and form a bond. So the name and formula of the compound that results, again, none of you guys should hopefully be surprised, is going to be Mg3N2. And of course, we call this magnesium nitride. And again, this diagram just kind of shows how that happens by the transfer of electrons. The last thing we're going to talk about here then is the energy involved in forming an ionic compound. So again, we've talked about how a metal will lose electrons, a nonmetal will gain electrons. So for example, if you are forming sodium chloride table salt, sodium will lose its electron and chlorine will gain an electron. But here's the problem. If you actually look at the energies involved in doing this, you have a bit of a problem because sodium, when it loses an electron, well, we have a name for that. It's called ionization energy. And it turns out it requires an input, that's what the positive sign here means, an input of 496 kilojoules per mole. Now, when chlorine gains an electron, right, we call that the electron affinity. In this case, you actually release energy. It's negative 349 kilojoules per mole. But here's the problem. If you just add these two things up, you'll notice that you'll get a positive number. That is the transfer of the electron from sodium losing the electron, and the chlorine gaining the electron, is going to actually be a net positive process, which means it's unfavorable. Right? So what's going on here, right? Because we know that when sodium and chlorine come together, they actually react, and they actually react quite violently and in a quite favorable manner to form table salt, sodium chloride. So on the basis of this electron transfer, it doesn't seem like that should happen. But again, this is where you have to remember that there's something else going on here. After the electron gets transferred, now this positive sodium and the negative chlorine attract each other. And that energy, that attractive energy, is going to actually be what tips the scales. So the transfer of the electron actually, a lot of times when you do the math, won't be favorable. It's going to be the attraction afterwards, the electrostatic attraction, that's really going to make ionic bond formation a favorable process. So how do we actually calculate this energy? We actually have to do it in a little bit of a roundabout way called a Born-Haber cycle, which I'll talk more about in a little bit. But first, I want to discuss a little bit more about this energy that you actually, energy of attraction between ions in a ionic compound. It's actually called the lattice energy. Now, lattice energy is actually kind of defined in the opposite way. Instead of thinking about the ions coming together, we think about it in terms of the ions splitting apart when you from an ionic compound. So let's say, for example, I have lithium fluorides, right? When lithium and fluoride come together, it turns out they're going to release a ton of energy. The lattice energy is actually defined the opposite way. It says if I have a lithium fluoride crystal or a compound, if I want to separate that lithium and fluorine apart into gaseous ions, right, what would that energy be? Notice it's just the opposite. So putting the ions together, again, that's a favorable process because they attract. If it's negative 1017 kilojoules per mole, then the opposite, trying to separate them apart, is going to be positive 1017 kilojoules per mole. Again, you have to put energy in. Right, so again, same idea here. One important thing to notice are the states of matter, though. Ionic compounds are generally going to be solids. They have very, very high melting points, typically thousands of degrees Celsius. And so to separate them, when you separate them, you're separating them into their gaseous state. So you're starting with a solid and you're separating them into gaseous ions. And again, this is going to be an endothermic process. So what are some factors that affect last energy? Well, for this, we're going to have to look at Coulomb's law. I mentioned Coulomb's law a few times this year, but Coulomb's law, the energy of attraction or of repulsion between two ions is given by this formula here, a constant K, which isn't very important for us in chemistry, and then Q times Q. Basically, these are the size of the charges on top, and then divided by R, that's the distance they are apart. So the charge times the charge divided by the distance that they are separated. So in the context of ionic compounds, Q plus is the charge on the cation, Q minus is the charge on the anion, and R is the distance between the ions. So one thing to notice in this formula is that the Q's are upstairs, right? They're in the numerator, which means that as the Q's get larger, as the charges get larger, then the last energy as well will also increase. This is simply saying that if you have bigger charges, there's more attraction between the ions. In the denominator, though, is the radius, or the distance between them. So in other words, if the distance gets smaller, if the ions get closer together, there's also going to be a bigger last energy. So to give you some examples of how this works, let's look at magnesium fluoride versus magnesium oxide. Now, the thing to point out here about them is if you look at their last energies, magnesium oxide has the larger last energy, but this actually shouldn't be surprising. Why? Well, both of them have magnesium, and magnesium has a charge of +2, right, as you guys know. But what's important here is that what's different are the charges on fluorine and oxygen. Fluorine has a -1 charge, oxygen has a charge of -2. In other words, magnesium oxide has bigger charges, +2, -2, as opposed to magnesium fluoride, which is +2, -1. And that's why magnesium oxide then is going to have the bigger last energy because it has that bigger charge. If I want to compare lithium fluoride and lithium chloride, though, notice in this case, they're actually both going to be +1, -1. So in this case, the charge is kind of a wash, right? They're going to have the same numerator, shall we say, upstairs in the formula. So what matters then is the denominator downstairs, the distance between them. So how do we figure that out? Well, it's going to have to do with the ionic radius. You're basically going to compare the ionic radii of lithium and fluorine to the radii of lithium and chlorine. Now, of course, the lithiums are just a wash. So I'm really just comparing fluorine and chlorine. And based on the periodic table, hopefully you know that fluorine, since it's above chlorine in the periodic table, is going to be smaller. Its electrons are in a smaller shell, n equals 2 as opposed to n equals 3. And so then it won't surprise you then that lithium fluoride actually has the bigger last energy. And that's because the distance between lithium and fluorine is smaller than the distance between lithium and chlorine. Now, of these two factors, again, this is a subtlety, you'll notice that the charge, Q, is the bigger factor. So between magnesium fluoride and magnesium oxide, you have a difference of about 1,000 kilojoules per mole. The difference between lithium fluoride and lithium fluoride, though, is much smaller, about 150 or 200 kilojoules per mole. So think about the charges first. They're going to be the more important factor. And then if you need more like a tiebreaker, then the distance is going to be the distance between the ions, which you can approximate using the ionic radii will be the tiebreaker. All right, so how do we actually find the lattice energy? Well, you actually can't find it directly. You can't find it directly. What we actually need to do is a bit of a roundabout way of doing it. So the idea here is the goal is we're trying to figure out how much energy it takes to separate sodium chloride, for example, or any ionic compound, into its ions, sodium and chlorine, Na plus and Cl minus. This, as it turns out, is very difficult to measure directly. So instead, what we do is we actually measure a whole bunch of other things. We actually end up measuring the heat of formation, and you end up measuring, let's see, some bond energies, some ionization energies, electron affinities, and when you put them all together, the idea is that you can kind of go in a roundabout way and figure out the last energy. So that's kind of what this chart is showing, is all these different energy changes. But what we're really after here is number 5 on this chart, because that's actually going to give us the last energy. So how then do we do this? How do you take a whole bunch of different reactions and kind of add them together to find an unknown reaction? Well, this, of course, is where we're going to bring in Hess's law. And so this cycle of different steps, of different reactions, if you call them that, is actually called the Bohr-Haber cycle, and it's really just an application or a specific case of Hess's law. So here's an example. I think this is easiest to illustrate with an example. Let's say that we're trying to find the last energy for barium chloride. And so to do that, what we're going to do is we're going to use all this information that they give us here in this table. So we have heat of formation, ionization energies, electron affinities, bond energies, enthalpy of sublimation, and so on and so forth. Now again, the goal, and don't lose sight of the goal here, is we're trying to figure out the energy needed for this process here, for barium chloride to be separated into barium and chloride ions. And again, notice the states of matter. It's barium chloride starting as a solid, turning into barium ions and chloride ions in their gaseous form, and we're trying to find delta H for this. And so the way we're going to find this is we're actually going to add up all the equations for the information in the table. Let's do this step by step. So the first one we have here is the heat of formation of barium chloride. Heat of formation is something that we talked about a couple of units ago. Heat of formation is the energy that you need to form 1 mole of a compound from its elements. So in this case, we're trying to form 1 mole of barium chloride from its elements. Those elements, of course, are barium and chlorine. Notice with heat of formation equations, the elements, in this case barium and chlorine, are in their kind of standard state states of matter. So at room temperature, basically, barium's a solid and chlorine's a gas, forming barium chloride solid. Right, and this process apparently takes minus 869 kilojoules per mole. Next thing is ionization energy. What's ionization energy? Ionization energy is about removing an electron. In other words, I'm starting with barium, and I'm going to take away an electron to form Ba+. Notice that ionization energy is in the gaseous state. That's actually the way ionization energy is defined. It's defined as a gaseous atom, in this case gaseous barium, losing an electron. Now this is the first ionization energy, removing the first electron, which apparently takes 503 kilojoules per mole. The second ionization energy then would be when that barium plus ion then loses a second electron to become Ba2+, and you can see that it's 965 kilojoules per mole. Electron affinity is going to be the opposite. It's about gaining an electron. So in this case, chlorine is going to gain an electron. Again, notice once again the chlorine is in the gaseous state, so it becomes Cl-. Bond energy, we haven't talked about this too much, but hopefully you just can kind of intuit what it means. If I have a chlorine molecule, Cl2, bond energy is the energy that you need to separate it into 2 separate chlorine atoms. In other words, it can be written this way. Cl2, the molecule, can then be separated into 2 chlorine atoms individually, and that apparently takes 239 kilojoules per mole. And then lastly, the enthalpy of sublimation. Sublimation is when the phase changes solid to a gas. In this case, barium solid turning to barium gas. It's 178 kilojoules per mole. Okay. And again, the idea here is I want to kind of add these up, kind of like we do with Hess's law, to find this last energy equation. Now, if you look carefully, we can't just actually add up what we have here. We are going to have to do some manipulations, shall we say. So for example, right at about, I see that BaCl2 is on the left-hand side of the equation, but in the kind of equations that we're going to manipulate, BaCl2 is actually on the right-hand side. So one thing I'm going to have to do right off the bat for this first equation is I'm going to have to switch the left and the right. Okay, so this one's going to have to flip. What else do I have to do? Well, I think a lot of the stuff actually will kind of already cancel out kind of nicely. I think the other thing I have to do though is I think I'm going to need 2 chlorides here, 2 chlorides, and chloride shows up in this fourth equation, the electron affinity. So I think I'm going to have to, at some point, double probably this equation here. Okay. So I think if I go ahead and make those changes here, right, so the first equation we flip it, and then the next 2 we can just keep the same. The fourth equation we doubled the electron affinity, and then the other 2 we kept the same as well. I believe if we add these up at this point, and again, we can kind of check it by canceling some things out, we should get what we want. So BaCl2, that's fine. Ba solid, that cancels out with this bottom one here. Cl2 gas cancels out with this Cl2 gas here. Barium in the gaseous state cancels out down here. Ba plus, Ba plus. Let's see, I have 2 electrons. Those are going to cancel out with the 2 electrons on the left here. And then let's see, I think there's one other thing to cancel. Yes, 2 chlorine gases, 2 chlorine gases. And actually, if you look at the only things that are left over now, I will have barium chloride on the left, and on the right, barium 2 plus and 2 chloride minuses, right? So again, you can see when I do that, I get my target equation, which is the definition of lattice energy. Again, what we really care about here, though, is the actual number. So essentially, most of these stayed the same except for that first equation, which we flipped. So that's why I put the negative sign on it. And the fourth equation, which we doubled. So I doubled the delta H value. You can then go ahead and add these all up. And when you do that, you'll get your answer here of 2,056 kilojoules per mole. So that is the answer. The lattice energy for barium chloride is 2,056 kilojoules per mole. We just had to find it in this very roundabout way using the so-called Born-Haber cycle.